Anyway, hello. Yeah, as mentioned, I'm Kurtis Heimerl, Associate Professor at the University of Washington, and I'm going to speak to Reclaiming Internet, a Journey to Community Health Cellular Infrastructure. As a brief aside, I want to describe my lab. I co-direct the ICTD lab at the University of Washington with this guy, Richard Anderson. This is a bit unique for the venue, I would imagine, but this lab focuses on technology and poverty alleviation and has been running and doing this for a long time. Richard focuses on kind of HCI topics, this being health, financial services, gender, and I work on universal internet access. There's some measurement study stuff and some ecological conservation work that happens as well. So to sort of start this talk, I want to go back in time and talk about the sort of founding of the internet. And this should be old hat to most people in the room, but I'll re-describe it anyway. If people may or may not know, the internet was originally founded as ARPANET, and the goal of ARPANET was really two things. First, survive a nuclear holocaust, which was successful, and two, to share resources, right? So basically the NSF would be giving supercomputers to places like the University of Utah, and they wanted other universities to have access to that. They didn't want to give everyone their own supercomputer. So we're going to build this big packet switching network of all these big computers in order to share those resources. And so the network was deployed and connected and grew, essentially connecting most of the academic institutions in the US. However, as the network grew, there's a realization it could no longer grow like this. And it became privatized in 1990. And as they did the privatization effort, they started forming standards to kind of define what they expected the internet to look like in the future. And what they did is they defined it as a set of autonomous systems that peer together at IXPs. The idea being, hey, what we're really going to have is small regional networks that interconnect, and that's the way that everything is going to grow, right? And you can see this in the protocols. Things like BGP really support this, the idea of an autonomous system and then interconnecting. Now, fast forward to today, and you see that that realization, that model has not really been the case. And this is the number of subscriptions for wireline internet in the US. And you can see it's dominated by three providers, Xfinity, which is Comcast, Charter, and AT&T, with a longer tail of smaller providers like Verizon that I'm sure you've heard of. This map is actually somewhat worse than it seems. Mid-continent in the Dakotas is actually Comcast, Time Warner is actually Charter. So it looks like a whole swath of maybe statewide connections is actually just the same big national players. And so you're like, okay, well, this isn't great, but like, okay, so what? Well, it's actually a little bit worse than this. So if you go to mobile, which is the most common way that people both in the US and internationally get internet access, you see it's like a strict three players. Verizon, AT&T, and T-Mobile, each kind of splitting up the market in the US. So we have a straight up triopoly here. And this repeats internationally. If you go to China, there's three players, China Mobile being the dominant one with almost 1 billion subscribers. And even other places, it goes all the way down to two, MTN and Airtel in Rwanda as examples. So, okay, maybe this isn't the way that we wanted the internet to be, but it works, right? Like a lot of people are online, and this is true. This is a somewhat aged graph, but I haven't been able to find a good replacement for it. What it's saying is basically like, there's a lot of people on the internet, and that continues to grow. We're over 4 billion, approaching 5 billion now, I'm sure. And so lots and lots of people on the internet. That's great, right? Like this model is working. And that's true, but it's working for some people and not working for other people. If you go and you see the rate of change, you see that's dropping, and it's dropping pretty fast. The idea of here being the low-hanging fruit, the easiest people to connect are getting online. But the people outside of that, for a whole wide variety of reasons, are not getting connected, and it's harder and harder to connect them. And so basically this model, these triopolies, duopolies are working for most people, but leaving out large elements of the population. This is best, I think, phrased in a GSMA report from 2016, where they said, in most countries, even in Africa, mobile operators have already rolled out 2G and 3G network coverage as far as possible within the envelope of a commercially sustainable business model. When they say a commercially sustainable business model, what they really mean is these monopoly, duopoly, triopoly models of access. And so essentially, if you're one of the 3.5 billion people without broadband, that growth is slowing. It's harder and harder to roll those networks out, and companies are more likely to install 5G in the dense urban core than continue to roll out access networks elsewhere. And if you're one of the 800 million people without any access at all, they're not coming. If there's not a 2G network, they're not going to be putting in a 4G network anytime soon. This is all caveated a little bit by Starlink, which is a discussion that we can have, which changes the dynamics a little bit, but not as well as I think everyone would have hoped. Instead, my research and the research area I work on is on community networks. And this is one potential solution to this problem. Community networks are networks built, owned, and operated by users in participatory and open manner. The idea being we get people to build these networks within the community, and then they build it for their own needs. They're able to optimize it or leverage local resources to be cheaper and provide local services. So really the idea being like highly localized networks that are built from the people in the area. Essentially, at the end of the day, this allows us to retake the distributed nature of the internet, build a lot of small regional ISPs that are community networks, and then interconnect those. And this may seem really like high-minded, but there are large success stories in the community network space. Wi-Fi.net is the big one, over 35,000 nodes in Catalonia. Others, NYC Mesh is the largest one in the US, serving a bunch of people in New York. There's Freifunk in Germany, Ultramundi in Argentina, Rhizomatica in Mexico, lots and lots of examples of this model working. My particular chunk of this is a thing called the community cellular network. And this is the application of cellular technologies to community networks. I do this because essentially my work at its core focuses on rural areas traditionally. And that's because I'm from Alaska and that's what I know. And cellular networks are really good for rural networks versus Wi-Fi networks, which is how most community networks are built these days. They provide wide area connectivity. Handsets are tier 1 clients with SIM cards and all that kind of stuff. And so they're really great for that particular problem space. And I've been building them for a long time. On the far left is my first installation of a 2G network in rural Indonesia. Then is a set of networks we deployed with the University of Philippines in the Aurora province of the Philippines. Middle left is a Rhizomatica network. And then we start to step into some of our more recent installations. This is the Seattle Community Network, which we're all going to hear about. Some work with tribal communities, helping do education on how to install networks. And then our most recent network on the far right in Ulukhaktak in the Canadian Arctic. And these are LTE networks. So we've been deploying these things for a long time and exploring this as a research area. And it's actually a pretty exciting time to be doing this. We had been limited by a number of really hard and messy technical problems for a long time, but these are being resolved. Notably, spectrum has gotten so much better. It used to be the case for the Philippine network, for example, that we had to work with a telecom, Globe Telecom, to be able to run cellular equipment in country. That's because all the 2G licenses were taken up. But here in the US, the Citizens Broadband Radio Service has really opened up this whole space for us. There's quality cellular spectrum available, and we use this in the Seattle Community Network. Similarly, hardware has gotten much, much cheaper. It used to be circa $8,000 for a low-end 2G base station. And right now I can buy an LTE base station for like $3,500. And this is going even lower. I've seen startups do come as one with an $800 price point for their radios. Basically, things like Open RAN and a general commoditization of the space because of standards and because of private LTE are making this equipment significantly cheaper, and we're trying to ride that into the future. And lastly, there's been a lot of motion in open source telecom. I was one of the original developers of OpenBTS. I say original, I sort of glommed onto the project at some point. But it was gnarly and very unspecified. But if you look at LTE and 5G, there are numerous core network solutions that are performant and useful. We use Open5GS for our networks, and it's great. We use it in prod. So really, there's been a big motion in all of these spaces, making this much easier. At the end of the day, the point here is just to say there's really a great opportunity for LTE and 5G community networks going forward. And so I'm going to talk about a specific project that we're working on in this space called cooperative cellular. The question that drives cooperative cellular is the following. While most of this work has happened in rural areas, how can we make community cellular appropriate for cities and urban areas as well? And you might ask immediately, well, why would you do this? There's pretty good connectivity in cities. And this is true. If you go, the city of Seattle had a survey and found 95% of people in my home city have access to the internet. But 95 is not 100, and indeed that last 5% is the kind of population that we like to work with. You can see here, they did some breakouts of this. It's people living in poverty, it's people living with disabilities, it's English as a second language, it's older people, it's racial and ethnic minorities. All these folks are disproportionately unlikely to be on the internet, comprise that 5%. And so the Seattle Community Network is working to bridge that gap by building free and low-cost LTE access network throughout the city. We're trying to connect people who can't afford to pay for access networks, can't afford to pay for user devices, and maybe just don't have the knowledge to be able to use the internet. And so we do this with a whole bunch of partners, just to call this out, notably Black Brilliance Research, Tacoma Public Library, Tacoma Cooperative Network, and again, a bunch of others. We deploy networks. We actually deploy live networks that serve customers in the region. Here are a set of our installations, exactly the kind of community centers I spoke to: a Roma Cultural Center, the Filipino Community Center, local high schools, Garfield and Franklin, local libraries, the Skyway Library in unincorporated King County, Tacoma Public Library down in Tacoma, and so on. The technical vision of what we're trying to do here is really take these organizations, let's say the Filipino Community Center, and let them connect their communities, right? They're extremely well situated in the communities that they work with and are able to be high touch and engage with them to get them online. This is basically the model we've been using for a long time. And what we've learned is that it does have a limitation. And that limitation is that these organizations don't want to become ISPs. Right? They want to connect the populations around them and they want to connect their constituents, but they don't want to grow. They don't want to become a regional MNO. That's like a pretty big ask and well outside their technical domain. You could do it. They could raise money for it. All these things are possible and organizations have done it, but it's rare and it's hard. And this makes scaling really hard, right? So what we do in this project is instead of scaling vertically, like making a really big network, we want to scale horizontally, make more networks, and then have them work together to provide coverage. And so that's what I'm going to talk about. We are building a stock UE compatible federated core network that allows for multiple small community sites to partner together to provide wide area coverage. It looks a little like this. On the top, you can see a traditional MNO. It'll say red is AT&T and green is T-Mobile, right? And they have overlapping, but not entirely overlapping coverage. There's places where AT&T is better, there's places where T-Mobile is better. On the bottom, you have our cooperative cellular model, where in this, there are dozens to hundreds of small networks, each interconnected over some software that we write. So again, in a traditional model, competing coverage, different coverage in different areas. In the cooperative model, what we do is we weave them all together to look like one big network. And so this provides us dense coverage and redundancy. Critical to this is how you do it, right? In a traditional network, users only connect to their home network. If you're an AT&T subscriber, you don't roam onto the T-Mobile network except under emergency circumstances. Now, in our network, we want to make that more common. Basically, you move, even if you're a Filipino Community Center subscriber, you can move to any other network in our network and get service and do that regularly. And so we built a solution called DOF to allow this. The goal of DOF is to allow users to move between these different community cellular sites while also allowing us to scale out to more networks. And in doing so, we came up with 3 design requirements that we had. The first is that we need to build a network that tolerates a failure of a subset of the nodes. Essentially, we're going to be running on small edge hardware with small community organizations. There's going to be downtime. We can't get the 5.9 expectations of a traditional telecom from these kind of organizations. So instead, we want to densify and fail over to other nearby networks. And that'll give us the kind of uptime that we're shooting for. Second, the trivial way to do this is simply share the network state, the user's key, for example, throughout the network. But this is really unsafe. You don't want to do that for a whole variety of reasons, including user spoofing and a whole bunch of other stuff, right? So we need to find a mechanism to do this that doesn't share critical network state across the network. And lastly, we need to support off-the-shelf devices. We can't expect people to buy new devices or make any kind of weird bespoke solutions. So, okay, what does DOF look like? So this is traditional roaming, right? And it is what you've experienced, I'm sure. You have a large centralized core network. This runs in a data center somewhere. Ours is in North Seattle for AT&T, that handles hundreds of thousands of subscribers, right? And in this data center is stuff like your home, your network key and all that kind of stuff. Now for roaming in this network, Imagine you're a British telecom customer and you come to Seattle. What you'll see is, that the AT&T network here builds basically an IPsec tunnel back to British Telecom, where your information is authenticated. This is great, but it doesn't really work for the kind of really fast roaming that we need to do, especially when these networks can go down. So here's DAuth. First, the idea of this is to say that each community will get a small core network. This is running open source software on edge compute hardware, supporting tens of subscribers, right? And so, for example, here at the bottom is green, our home network. This is the one that holds our keys. Here's our serving network. This is the one that's providing a service at the moment. And then there's like a whole bunch of other networks in there, right? Now, what we do is we let the home network generate authentication vectors, is what they're called. These are pre-computed tokens which allow a user online. They're basically for caching and speeding up a traditional network. They're cached at the enode B so that a user can land and authenticate quickly. But we pre-compute these and push these out into the network, into a set of backups as decided by the home network. But critically, this does not include private information like your key. In this, then, if the home network is down, the serving network can reach out to one of these backup networks and get access. And they're able to move forward. Now, the last piece of this is that there's a public distributed directory of these networks so that you can find who's online and who you want to connect, or what backup networks are available. This is a little hand wavy, but the critical point here is to say that this allows for low-cost hardware and small community networks while maintaining the expected network resilience and performance that we've seen before. So we evaluated this. You can imagine, basically, the performance is going to be lower than a traditional EPC because there's like an indirection step, but it largely depends on the properties of the peers. If there's a lot of them, we can get to them fast. If they're close via like network close, we can get faster responses. So hairpinning through local IXPs and all these things is problematic, but you can design a network where this will be more than performant enough. Lastly, I want to end on the social elements of this network. While we do internet access, we also do a whole bunch more. And this includes service learning and capacity building in the network. This is stuff like hack nights and discotheques, and a thing we call digital stewards, which is a youth and adult vocational training system where we teach people about networks and build that capacity so the network can sustain itself. There are youth and adult versions of this with hands-on computing education on internet infrastructure, the principles of networking, and community organizing principles. So here are 3 of those cohorts here in Seattle. And critically, while the network itself provides internet access and provides this, we view it as something of a teaching network, akin to a teaching hospital, if you've heard that. Basically, these digital stewards both build our network and help us maintain the network, and also travel places and help other people learn about networks. This is the Tribal Broadcamp Bootcamp, where some of the digital stewards came and taught about networks. Building a community practice on the day-to-day operations of running this kind of infrastructure. I'm seeing a lot of thumbs up, so I know I'm in a hurry. In conclusion, we believe the internet and specifically access networks should be more distributed, and industry is helping us do that at the moment. So we're building this cooperative architecture to weave community infrastructure together and to build out a kind of brand new type of NO. Thanks everyone, and I'm happy to take any questions.